how the chain rule actually works, we might have dp over dt, and we can write this as negative p times u over du times du over dt. So that would be our chain rule here. And we have done this first part here. Now we need to do the differentiation of this second part here. And we said this du, that would be the differentiation of this part here. So we need to differentiate this part here, e to the minus kt. And so if we do differentiate this, we would get minus k times e to the minus kt. That is the rule for the differentiation for this one here when we differentiate that for dt. So what have we got now? It looks all very complicated, but the solution is surprisingly simple, because when we do dp over dt and we apply this chain rule, what we actually get is minus the concentration when we wait very long times minus k times e to the minus kt. So that would be our rate in general. Now we evaluate this curve for t equals 0. So t equals 0, that is our starting point. T equals 0. What do we get? Now, we get, of course, this same equation here. But what would happen if we put in t equals 0? So we would have, let me write this down here, dp over dt. That's our gradient here. At the time 0 would be minus p when we wait very long, times minus k times e to the power of minus k times 0. And that would give us 0, and anything to the power of 0, that would give us 1. So our gradient here at 0, so dp at the time 0, would be just simply minus p0 times negative k, because this term here equals 1, and that would just simply give us p0, or p at the time when we wait very long, times k, because the negative signs eliminate each other, cancel each other out. So the gradient that we are looking at, the production per time unit, is just simply our final amount of the GFP times the rate constant. Now, of course, we now have a slightly different problem, because now we need to find out what is the rate constant. And how this is done is I'm going to show in the next video.